Hello friends, welcome today's lecture Stresses in Beam. Myself Mr. Y.S. Patil, Department of Civil Engineering, Sharad Institute of Technology, College of Engineering, Yadrao. In last lecture we studied about bending stresses. Basically bending stresses find out by using flexural equation, that is M upon I, sigma upon Y and E upon R. So equating these equation we can find out stresses in the beam. So let us see problem on the same. A rolled steel joist of I section has the dimension as shown in figure. The beam carries a UDL of 40 kN per meter run over span. Calculate the maximum stresses produced due to bending. So in this problem, the section is I section and the dimension is like this. The overall depth of this I section is 400 mm, width of the flange is 200 mm and depth of the flange is 20, and the section is symmetrical. So top flange and bottom flange are same dimensions. Then UDL of 40 kN per meter over a span of 10 meter. So first of all we calculate moment of inertia about XX axis, that is IXX. We know the IXX for rectangular section, that is BD cube by 12. So this is the I section. So first consider this overall rectangle, that is dimensions B is equal to 200 mm and D is equal to 400 mm. So first 200 by 400 cube divided by 12. This is the overall rectangle and minus these two parts. The dimension of these two parts is overall dimension of the overall width of this section is 200 and thickness of web is 10. So width of this cross section are 200 minus 10 and depth of this section is overall depth is 400 mm and minus thickness of top flange and thickness of bottom flange. So 400 minus 40. So it become 360. That is net moment of inertia is equal to 200 into 400 cube divided by 12 minus 200 minus 10, that is 190 into 360 cube divided by 12. So this is the moment value of moment of inertia with respect to XX axis. Then next calculate maximum bending moment. So for maximum bending moment, if beam is simply supported and carries a UDL over entire span, the maximum bending moments become WL square by 8. So W become 40 kilonewton. So convert into Newton, that is 40 into 10 raised to 3, that is 40,000. L square, that is 10 square divided by 8. So this moment is equal to 5 into 10 raised to 8 Newton mm. This is the moment of inertia I and this is the maximum bending moment M. Then we know the equation, that is flexural equation, M upon I is equal to sigma upon Y. So already we calculated M and moment of inertia I. So we want to calculate sigma max and we know that the sigma max value is depends upon Y max. Already in last lecture we discussed about the sigma max depends upon Y max value and the maximum stresses produced at the top fiber of the beam from neutral axis. So this is the distance and this is a symmetrical section. So top that neutral axis lies at the overall depth divided by 2, that is 400 divided by 2 means this is the 200. Okay. So sigma max is equal to M upon I into Y. So M is equal to 5 into 10 raised to 8 divided by, this is the moment of inertia value, into Y max, that is 200. So sigma becomes 304.92 Newton per mm square. And at top and bottom both values are same, means this is a 400 and from the top fiber is 200, bottom fiber 200. So sigma becomes at tension as well as in compression same value, that is 304.92 Newton per mm square. The next problem, A cast iron bracket subjected to bending has cross section of I from the unequal flange. The dimension of the section as shown in figure. If the maximum bending moment is 40 meganewton mm, determine the maximum bending stress. So this is a cantilever section, okay, and bending moment on that section is 40 meganewton into mm, and the dimensions are, this is the unsymmetrical section, means top flange dimension is 200 by 50, web is 50 by 200 and bottom flange 130 by 50. So we want to calculate first moment of inertia, and before starting to calculate moment of inertia, we want to locate the center of gravity, that is x axis. Okay, so we want to calculate y bar. So y bar is equal to, suppose this is section number 1, section number 2 and section number 3. This is a means 130 by 50, 50 by 200 and 200 by 50. This is section 1, section 2 and section 3 respectively. So first y bar is equal to, how to calculate y bar? A1 y1 plus A2 y2 plus A3 y3 divided by A1 plus A2 plus A3, where A1 is equal to area of this section number 1. Section dimension for section number 1 is 130 by 50. So A1 becomes 6500 mm square. Then Y1 is CG distance of this section number 1 from bottom of the section. This is our reference line. So whatever the Y1, Y2, Y3 calculated from bottom of the section. So depth of this section number 1 is 50. So Y1 becomes 50 divided by 2, that is 25 mm. Then next moves towards section number 2. The dimension of section number 2 is 50 by 200 mm. So area becomes 10,000 mm square. Then CG of this section number 2 measures from bottom of the section. So depth of section number 2 is 200 mm. So CG for this section number 2 is 200 mm. Up to 200 divided by 2, that is 100 mm. Means this is the 100 mm. But we required CG from bottom of the section. So add 50. So that is 50 plus 200 divided by 2. That is 150 mm. It is value of Y2. Then next move towards section number 3. Dimension of section number 3 becomes 200 by 50 mm. So area, that is A3 is equal to 10,000 mm square. Now CG, that is Y3, CG for this section number 3 from bottom of the section. We know the depth of the section is 50 mm. So CG becomes 50 divided by 2. This is the CG. But we want to distance from bottom of the section. So we add this point to this point. That is 200 plus 50. That is 250 plus 50 divided by 2. That is 50 plus 200 plus 50 divided by 2. The value becomes Y3 is 275 mm. Then we know the equation for y bar, A1 y1 plus A2 y2 plus A3 y3 divided by A1 plus A2 plus A3. So put up all A1 y1, A2 y2, A3 y3 and A1, A2, A3 value in this equation and solve this equation. We got y bar is equal to 166.51 mm, and that distance is measured from bottom of the section, means that 166.51 distance become from bottom of the section. This is the y bar. Okay. Then next we want to calculate moment of inertia. So tabulate all values, that is say bottom flange dimension is 130 by 50, A1 6500, Y1 becomes 25. Whatever the all values for wave and top flange is mentioned in this table. So y bar is equal to 166.51 is there mentioned here. Okay. Then Ixx is equal to, I want to moment of inertia about this x axis. So Ixx is equal to moment of inertia for section number 1 plus moment of inertia for section number 2 plus moment of inertia for section number 3. But this is an unsymmetrical section, so moment of inertia is different for all, means that center of x-axis is different for all three section. So I1 is BD cube by 12 plus AH square for section number 1. Second, BD cube by 12 plus AH square for section number 2 plus BD cube by 12 plus AH square for section number 3. This is a B and D for section 1, 2 and 3. This is the section number 1, this is section number 2 and this is section number 3. These values are B, these values are D. Okay, this is the A1, A2, A3. Now one more is how to calculate H1, H2 and H3. H1, H2, H3 is nothing but difference between x-axis for section number 1 and final, that is x-axis for composite section. Means suppose this is the x-axis for section number 1, that is y1 25 mm. So I want to, H1 means nothing but the difference between these two axes, this and this. So how to calculate H1? H1 becomes y bar minus y1. Y bar minus y1. Already know the y bar value 166.51 minus y1 is equal to 25. So H1 becomes 141.51. Then next H2 means difference between section number 2 and final x-axis, means y bar minus, this is the y2 value, y bar minus y2. Y bar is 166.51 and y2 is 150. So H2 becomes 16.51. Then H3 is difference between these two axes. So H3 is y3 minus y bar. So 275 minus 166.51. So H3 becomes 108.49 mm. So put up all values for corresponding section, that is section number 1, section number 2, section number 3. Already we know the B value, D value, area and H1 for section number 1, same for section number 2 and same for section number 3. Put up all values in this equation and calculate moment of inertia, and the Ix value becomes 2.84 into 10 raised to 8 mm raised to 4. This is the moment of inertia for composite section. Okay. Now see here, overall depth of the section is, the depth of the section number 1 is 50, the depth of section number 2 is 200 and depth of section number 3 is 50. So overall depth top to bottom is 50 plus 200 plus 50, that is total depth is 300. Okay. Then we know the value of y bar is 166.51. So we can calculate remaining distance, that is 300 minus 166.51. So that value becomes 133.49. Means this is the cantilever section. At the cantilever section, the stress distribution like diagram like this, and this is the your YT and this is your YC. Means this value becomes YC and this value becomes YT. By using this YC and YT, we can calculate sigma C and sigma T. So let us see how to calculate stresses in compression as well as in tension. So equation, flexural equation is common, that is M upon I sigma upon Y. Already M is given, that is 40 into 10 raised to 6. This is the M value, and 2.84 into 10 raised to 8. This is a moment of inertia. So sigma C and sigma T depends upon YC and YT value. That is, this is your YC and this is your YT. So sigma C and sigma T depends upon this YC and YT value. So sigma max is equal to, for compression, that is compression stress, is M upon I into YC. So YC becomes 166.51, and simplifying this equation, we got sigma max is equal to 23.4 37 Newton per mm square. Similarly, calculate stress in tension, that is M upon I into Yt. This value is Yt is there mentioned. So 40 into 10 raised to 6 divided by 2.8 into 10 raised to 8 into 133.49. So sigma T becomes 18.80 Newton per mm square. This is the tension stress, this is the compression stress. Consider baseline and mark this is your neutral axis. At neutral axis bending stress become 0. So at tension value is 18.80 Newton per mm square and at the compression 23.37 Newton per mm square. Join straight line. This is your compression, this is your tension stress. This is the solutions for unequal flanged or unequal section. Thank you.